It's my pleasure to introduce Dr. Alex Tetarenko from the East Asian Observatory in Hilo, Hawaii. Alex earned her PhD from the University of Alberta in 2018. For her thesis, she was awarded the 2019 Plaskett Medal from the Canadian Astronomical Society, which is awarded for the top thesis in Canada in astronomy over the previous 2-year period. She has spent the last 3 years as a fellow at the East Asian Observatory, and she has been selected for an Einstein Fellowship, which she will start in October at Texas Tech. Her work has revolutionized approaches to understanding relativistic jets from compact stellar objects by using the variability. And Alex will present to us today a talk entitled Unraveling How Black Holes Power Explosive Outflows with the Time Domain. So without further ado, I now turn control over to Dr. Tetarenko.
All right, cool. Thanks very much, Tom. And thanks very much to the organizers for inviting me to speak with this seminar series. So today, I want to talk to you guys about how we can use the time domain to study jet and accretion physics in stellar mass black hole systems in our galaxy. In particular, I'm really going to focus on the transformative role that instruments like the VLA and ALMA have played in being able to do this kind of science in the radio bands by highlighting some recent exciting results on a few different systems, as well as providing a bit of a future outlook on what's to come with next-gen instruments such as the ngVLA. And this work is done in collaboration with a bunch of very awesome people, all listed on the slide there. So before I get into all the details of how we can do fast timing in the radio on these stellar mass black hole systems, I want to first kind of briefly outline the science motivation for these kinds of data. In particular, why it's important to understand accretion-driven jet phenomenon and why these stellar mass black hole systems are really the best way to do it. So determining how jets arise and quantifying the energy they carry, these are important multifaceted problems in astronomy, with implications for other areas of physics as well. For instance, we know that jets have a fundamental effect on their environment, where injected energy can alter the chemistry of interstellar gas, in turn influencing large-scale processes, such as the formation of stars and even the evolution of entire galaxies. Black holes and their jets also provide unique laboratories to start probing fundamental physics beyond Earth-based experiments. For example, in creating the first ever image of a black hole, the Event Horizon Telescope has performed some of the most stringent tests to date on Einstein's theory of general relativity. Additionally, jets also come into play within the exciting new areas of multi-messenger astrophysics. For instance, one of the most promising ultra-high energy neutrino candidates are actually the jets launched from supermassive black holes. So these jets are everywhere, but despite their prevalence and their importance in our universe, we understand an embarrassingly little amount about them and their fundamental properties. In particular, some of the really key unknowns are launching and acceleration mechanisms, what it actually looks like in that key launching and acceleration zone, what role do black hole mass and spin and accretion rate actually play in producing these jets, what actually drives jet evolution, where do magnetic fields come in, and of course, how do we quantify the energetics of these outflows? Now, our best chance to actually start getting some concrete answers to some of these questions doesn't mean we necessarily need to be studying the big supermassive black holes, like all the examples I just showed you a few slides ago, because it turns out that the smaller stellar mass ones that exist in X-ray binary systems in our galaxy are actually much more ideal test beds for studying jet phenomenon. And this is because they're numerous, they're close to Earth, and they evolve on human timescales, where the majority of these systems are actually transient, progressing from periods of minimal activity into these bright outbursting states on timescales of days to months. This essentially means that we can probe many more dynamical timescales and ejection cycles in these stellar mass systems when compared to their supermassive counterparts, and basically watch them change in real time by tracking one of these outbursts. Now, to give you an idea of what one of these outbursts actually looks like, typically these sources will transition through several different accretion states as they evolve from a quiescent quiet state into outburst and back again. Now, we can visualize this kind of evolution on what we call a hardness intensity diagram, or an HID, and that's what you see here on the right side of the slide. Here we have X-ray luminosity, which essentially acts as like an observational tracer of mass accretion rates, increasing upwards, and X-ray hardness, which is basically the ratio of high energy to low energy emission, increasing to the right. And black hole X-ray binary systems tend to follow a Q kind of type pattern in this plane. As the system leaves this quiet quiescent state, it tends to start in a lower luminosity hard state, where we have a compact steady jet. We also have some optically detected accretion disk winds, which is another type of wide angle outflow we see in these systems. We have an accretion disk and we have a hot inner accretion flow. Now, as the X-ray luminosity rises, this steady jet continues to build up. And as the X-ray spectrum starts to soften, so we start going towards the left of this diagram, the jet velocity is thought to increase. And this means that the jet's going to start becoming unstable. Now, eventually, we'll get to a phase where we transition from a harder state to a softer state. This compact jet will be suppressed and it'll be replaced by some much more spectacular versions of these jets. Basically, they're these discrete jet ejection episodes, which we can actually resolve with VLBI and tend to manifest as these quite spectacular flaring activity in light curves. Now, the ejector will fade at some point and will be totally in a soft state with no jet at all. And then eventually the X-ray luminosity will drop once again. Our compact jet will be reactivated as we go back to the hard state. Although this time we won't see the fireworks again, we won't see any flaring and we won't see any ejections. So the bottom line that I want you to kind of get from this slide is that all of this is happening over timescales of months. So we're seeing a range of luminosities, hardnesses, jet behavior, all in one single system. So that gives you an idea of how important these systems can be in trying to understand this jet ejection phenomena. So how do we actually study these jets? Well, we're mostly radio astronomers here, I imagine. So the most obvious method that you'll think of is, well, direct imaging with VLBI. And you'd be correct. This tends to be a really effective method, especially when looking at those jet ejection episodes and really trying to connect how those ejections are happening with what's happening in the accretion flow. In particular, what we can do is we can essentially resolve these ejections with VLBI, track their motion, and then work backwards to estimate the ejection dates. And this is a really key thing to pinpoint, because once we do, we can start looking for signatures in the accretion flow properties for this jet launching. And on the bottom of the slide here, I have an example of some recent work by Tom Russell and collaborators looking at the system MAXC 1535. And here you see the motion of an ejection that we tracked over several months. And what's really interesting is when we track it back to the ejection date and look what was happening in the X-ray emission probing the accretion flow, it seems to become really close to a specific X-ray timing signature that we call a quasi-periodic oscillation. And this has been seen in a couple other systems as well. So that's quite exciting find. Now, we can also use VLBI to resolve some of these compact jets as well that I told you happen at more lower luminosities during these outbursts. Although we're really limited by our resolving power here, and we've only been able to resolve these jets in 3 systems, I think, by now, and it's only ever along the jet axis. Now, beyond just imaging, a full kind of broadband view of these systems can also be very beneficial, especially in examining the relationship between the jet and the accretion flow. So you can imagine doing photometric observations across the electromagnetic spectrum to build up a nice broadband jet spectrum. Now, as you might expect, given how dynamic these systems are, the jet spectrum is definitely not static. It tends to evolve over time. And what actually happens, example I show you again from this system MAXC 1535 on the left side of the slide, you can see that what the spectrum tends to be represented by sort of this broken power law type form. And what we end up seeing is that break in the spectrum tends to move to lower electromagnetic frequencies as we move to higher mass accretion rates. So going sort of up the side of that HID diagram I showed you before. And pinpointing where this break is actually really important because we think that it actually represents the jet phase where particles are first accelerated to high energies. And what's really exciting is that recently there's been found a correlation between this jet spectral break and the X-ray spectral properties. That's what you see here on the right of the slide. And this essentially means that we're basically linking properties of the plasma close to the black hole and particle acceleration properties in the jets, and suggests that this sort of changing dynamic spectrum that we're seeing is actually driven by changing accretion flow properties. And this really gives us a good way to try and understand how the jet responds to the accretion flow. Now, these are both great ways to study jets. But it turns out that time domain observations now offer a promising new way to address some key open questions in jet research that we just can't quite get at with those other two methods. For example, we can probe physical size scales not accessible with current imaging capabilities. And to really put this into context for you guys, timing studies of X-ray binaries can uniquely accomplish science that VLBI simply cannot. We can go beyond even the scales that the Event Horizon Telescope could image if we pointed it at an X-ray binary and zoom in close to the black hole where these jets were first launched and accelerated. The time domain also allows us to probe notoriously difficult to measure quantities like energy output and speed. And by comparing variability signals across different wave bands, we can begin to link changes in our accreting material probed by the X-ray with changes in the jets probed by the longer wavelengths, thereby mapping out the sequence of events leading to jet launching and particle acceleration like we've never been able to do before. So, given their incredible diagnostic potential, time domain studies have been used extensively to study accretion around these stellar mass black holes at X-ray wavelengths. However, it's really only recently that technological advancements have made it possible to do these kind of timing studies in the jet-dominated longer wavelength part of the electromagnetic spectrum. Now, the first exciting advances in studying jet variability in these X-ray binaries came in the optical and infrared. And it was due largely to the invention in the early 2000s of these new fast readout detectors that essentially allowed us to start probing sub-second timescales in these bands, getting closer and closer to what we are already capable of doing in the X-ray. And the first unambiguous detection of fast variability from one of these compact jets came from the system GX339, where significant variability was detected in the optical and infrared on sub-second timescales. And it was found to be highly correlated with the X-ray. And that's actually what you see here on the left side of the slide. This is a cross-correlation function comparing the X-ray and infrared signals in this system. And you'll notice it peaks at about 100 milliseconds. That tells us there's about a delay of 100 milliseconds between these two signals. Now, this study was quite important as it was really the first suggestion that variations in the accretion flow probed by the X-ray could subsequently be driving variability in the jet, probed by the infrared in this case. So it was really kind of a proof of concept for this science. And this science with optical infrared variability has really progressed over the last decade or so, where now we're at the point where we're able to look at much more sophisticated Fourier domain metrics to quantify our variability. And what's really cool is that some recent studies have actually shown that we can start reproducing these Fourier domain timing metrics like the power spectra, the coherence, the phase lags, all with state-of-the-art jet models. And this means that it opens up the possibility to be studying detailed physical processes that happen inside the jet through just the analysis of variability alone. And that is incredibly powerful. So what about the longer wavelengths? Well, we have known for a while that radio jet emission is highly variable in these systems. But while the longer timescale variations have been tracked and well characterized in many systems, this is really not the case for the short timescale variations. So I'm talking less than a day, less than an hour, for which up until a few years ago, there was really only a handful of detections. And even in these handful of detections, there was little effort to really analyze this kind of short timescale variability. And to give you guys an idea of what I mean, up until a few years ago, the only radio frequency Fourier domain study of one of these systems was this Napodi et al. 2005 study, where the shortest timescales they probed were only days. So really the reason for kind of like the lack of study in this area up until, the last few years is the fact that these kind of time resolved observations, they're such a staple for the X-ray and even the optical and infrared these days. But there are many more challenges that we face in trying to do these at the longer radio and submillimeter wavelengths. In particular, it can be difficult to disentangle intrinsic source variations from atmospheric or telescope gain variations. Observations often involve routinely cycling between observing a target source and a calibrator. And in most cases, we're only observing at one waveband at once. And these obstacles are going to prevent things like continuous observations of the jets. They could introduce artificial periodic signals into the data. All of this is going to complicate a time domain analysis. Further, until recently, most telescopes were not even sensitive enough or capable of taking this kind of rapid data that we really needed. Luckily for us, all is not lost, because with today's more sensitive interferometric arrays, for example, the VLA, which offer much more customizable and flexible observing modes, we can start lifting some of these limitations and start accurately sampling X-ray binary jets at radio frequencies in the time domain. But unlike the optical and infrared, where sort of timing studies, the catalyst for doing timing studies was these new, better instruments. Having a new, better instrument in the radio is not enough because of the extra challenges we face. We just have to get a little more creative with how we're using it. Now, in particular, one technique that's proven to be incredibly important in overcoming the limitations we face in the radio is the use of subarrays. So here, what we can essentially do when we have a large interferometric array like the VLA, we can separate it into individual subarrays, which each basically operate independently of each other. So you can imagine separating the 27 element VLA array into like a 10, 9, 8, 3 subarray split. Now here you could observe a different frequency band with each subarray, and then you're able to start sampling at 3 different regions of the jet all at once, and you've solved this simultaneous multi-band problem, basically giving you 3 different telescopes in one here. And you can imagine getting even more fancy and starting to sync up your subarrays to manufacture longer continuous bouts of data. And this is really important in giving you access to these really powerful Fourier domain techniques that I mentioned were very useful in the optical and infrared variability studies. So when it comes down to it, subarraying allows us to get the data that we need to take advantage of these timing techniques that have been developed for the X-ray, for the optical infrared, but now starting to apply them to the longer wavelength radio and submillimeter. So this is great in theory, but how does it actually work in practice? Well, our first attempt at doing this came back in 2015 during the outburst of B404 Cygni. Here we used 2 subarrays with the VLA, and we combined those observations with submillimeter from the SMA and JCMT in Hawaii. And this allowed us to sample these incredible flaring episodes that you see here on the left side of the slide. And these flaring episodes actually coincided with repeated jet ejection events, which you see resolved in the lovely movie on the right side of the slide. So these are these spectacular jet ejections that I was speaking about that happen at those higher luminosities right at the top of that Q-shaped HID. So this worked incredibly well, but this was rare and really bright phenomenon. What about a more typical quieter source? Well, a few years ago, we observed the system Cygnus X1. Again, we used 2 subarrays with the VLA, and this time we were able to combine it with X-ray observations from NuSTAR to allow us to try and make this connection between the accretion flow and the jet. But this time we got a bit more fancy with our subarrays. We synced them up in a way that we were able to manufacture a continuous bout of data for the first half of the observation in the higher frequency bands, and for the second half of the observation in the lower frequency bands. Now we do this because, as mentioned earlier, we expect that the higher electromagnetic frequencies are probing closer to the black hole and the lower ones farther out in the jet. So we expect the higher frequencies to peak before the lower frequencies. And once again, from the light curves you see, we're able to resolve this nice, beautiful flaring activity throughout. Now, recently, we kind of took this one more notch up. We really wanted to focus on connecting variability from across the electromagnetic spectrum. So we wanted to combine this successful subarraying technique that we've used on these previous 2 systems with submillimeter, infrared, optical, and X-ray, all across the electromagnetic spectrum. And we were able to do this with the system MaxG J1820 plus 070 recently, where we combined a subarray VLA. This time we're using 3 subarrays with ALMA, VLT, NTT, NICER, and XMM, giving us this killer combination of 10 different unique electromagnetic bands all at once. And over half of these bands came from a subarray VLA. So that just gives you an idea of how important that is in being able to do this kind of science. And once again, you see, we're able to resolve this incredibly beautiful variability all the way through all the bands into these kind of rapid flaring episodes. All right, so it's clear that subarraying can allow us to get these beautifully sampled data sets. Now I want to show you an example with this latest MaxG 1820 data set of what we can actually do with this and kind of deliver on my promise from earlier slides of probing jet physics with variability. So the first thing we need to do is we need to characterize the variability we're seeing in our light curves. This is what's going to allow us to start making these connections to jet physics. So we take a cue from X-ray and optical infrared variability studies, and we start in the Fourier domain. Now, by building power spectra of our data, that's what you see here on the right side of the slide, we noticed that there was a clear difference between the shape and the amplitude of the power spectra in the different bands, which are represented by the different colors. Notably, we see that the break in the power spectra after which the power becomes damped on the shorter timescales or higher Fourier frequencies seems to move to lower Fourier frequencies as we shift to lower electromagnetic bands. And this pattern is remarkably consistent with what's been predicted by theoretical models, like, for example, the internal shock model from Julian Malzak shown on the left side of the slide, where once again, you see power spectra from different bands in different colors. So to highlight these trends a bit more quantitatively for you, here on the left side of the slide, I show the power spectral breaks versus electromagnetic frequency, where again, you can see that clear trend come out. And I also show the fractional RMS, which is basically the variability amplitude at the different bands as well. And that's what you see here on the right. Now, all of the data points, they're color coded with the jet schematic on the bottom of the slide there to kind of give you an idea of where the different emission regions are coming from. So the trend in amplitude from the right side of the slide, this is easily enough explained by, again, we expect higher electromagnetic frequency emission to originate from a region with a smaller cross-section closer to the black hole. But the power spectral break, on the other hand, we believe, at least to first order, could be tracing the size scale of the emitting region downstream in the jet. And if we kind of think about this in terms of the theoretical model that I mentioned on the previous slide, this internal shock model, in this model, flux variability is driven by the injection of these discrete shells of plasma at the base of the jet with variable speeds. Now, the fastest timescale velocity fluctuations are dissipated closest to the base of the jet, as the most rapid variations have led to these shells catching up with each other rather quickly. Further downstream in the jet, only the more slowly varying jet velocity fluctuations still remain to catch up with one another, create shocks, and produce the varying radio emission that we're observing. As such, this argues in this kind of model framework that this power spectral break has to be related to the distance downstream in the jet, just like we had predicted. And in this sense, it seems that we're basically using the accretion signal as almost like radar or sonar to kind of map out the jet. And that's quite cool. Now, this is just purely looking at the amplitudes of the variability, but we also want to examine how correlated the variability is between the different wavebands. And this is something that is really key to what we're getting out of this subarraying technique, having this multiple simultaneous data all at once. So to look for these kind of correlations, what we can do is we can use cross-correlation functions, just like the optical and infrared variability studies that I showed you earlier, to look for lags or delays between the signals in different wavebands. Now, we expect the lower electromagnetic frequencies to lag the higher electromagnetic frequencies, again, because the lower electromagnetic frequencies are probing farther downstream in the jet. Now, so here on the slide, I show you clear radio lags that we have detected between the radio bands using just the VLA subarray data here. And you again see this trend with electromagnetic frequency. And it agrees with this idea that these lags must be tracing material propagating down the jet flow. Now, for anyone who knows the X-ray binary literature in the crowd, you'll probably say, well, lags, that's not a new thing. They've been detected for a while. But what's really different with these kind of studies that we're doing now is the fact that we can detect lags at multiple bands simultaneously. And this is really important when we want to actually connect this variability that we're seeing to real jet physics that you'll see in a moment. All right, so we've measured all these different timing metrics, right? We have lags, we have power spectral properties, and we get average fluxes for free. How do we actually make this connection to real jet physics? Well, it turns out we can predict all these quantities even with a standard compact jet model, where here we just have a continuous constant velocity conical jet. Particles are injected into the jet base and accelerated into power law energy distribution, producing the synchrotron emission that we're observing. The problem is that this model is kind of plagued with degeneracies. So if we try and just model any one of these individual timing metrics, we're not going to get much out of it. Luckily for us, if we can take advantage of Bayesian statistics, we can actually simultaneously model all these quantities, tying our jet parameters in our model across them all. We can include prior knowledge on independent measurements on things like distance and inclination. And this all allows us to start deriving meaningful constraints on key jet parameters. And that's what you see here on the slide. This is a best fit of our jet model to all our different timing metrics. And you can see we can reproduce them all quite well with a single jet model. And even better, if we go and look at an independent size scale measurement from VLBI, and we plop it right there on our break frequency phase space plane, even that's the light blue X right there, you can see that it agrees remarkably well with our best fit models. That gives us a little bit more confidence in what we're doing here. All right, so what is this model actually telling us about the jet? Well, we find that this jet in MAXI 1820 is highly relativistic, highly confined, and incredibly powerful. So just zoom in on the jet speed for a second here. What's really interesting is if we start comparing to the few other sources with speed constraints. Now, admittedly, there are 3 sources here, so take this with a grain of salt. But there are some tentative hints that we might be beginning to see direct evidence for jet speed being correlated with accretion rate, Eddington fraction. And this is something, if you remember way back from that hardness intensity diagram slide, that this is in this like model, phenomenological model picture that we have in our head of what happens during these outbursts. So if we could actually be seeing direct evidence of it, that would be quite cool. All right, so let's move on to the next bit. So we also find that a really small opening angle for this system, and that suggests a really highly confined jet. Now, it's difficult to pinpoint what confinement mechanism could be operating here, but if you think about it, we know that there was a really strong accretion disk wind. So that was that wide angle outflow that I told you about earlier that was detected during this outburst. So it is possible that this wind could played a significant role in inhibiting the transverse expansion of the jet. Now, the interplay between these 2 outflows, the winds and the jets, is not particularly well studied yet. So this is sort of a really interesting future direction to go in. Lastly, we found that the jet was incredibly powerful. Now, for the X-ray binary aficionados in the room, you might think, well, this is really reminiscent of systems like Cygnus X1. This system is thought to have a really high jet power as well, and is thought to have deposited a significant amount of energy into the local ISM. And in fact, it's believed that energy helped blow out this huge bubble cavity in the surrounding medium. So you might think that maybe a similar effect could be happening here in MAXI 1820. And in fact, later on in the outburst, X-ray hotspots were detected on either side of the system, which could be produced by shocks between an edge of some sort of ISM cavity and the jet. So that's quite interesting to think about as well. Now, if you're not an X-ray binary person, you might not be as excited as me about measuring all these properties. So really, the bottom line that I want you to kind of take away from this slide and really this talk is if we combine these state-of-the-art observational techniques like subarrays with the VLA, with this modeling formalism that we've developed, we're able to derive fundamental jet properties from just the light curves alone. And this is incredibly powerful. But there's still one problem with this. Now, the majority of these studies, these timing studies, they're all one-shot observations, like all the ones I've shown you today, only one time during an outburst. Thus, we're unable to probe how jets evolve over time through different stages of their outburst. And to really kind of put this into context for you guys, this is what our sub-millimeter coverage of this system, MAXI 1820, looked like. So you'll notice that it's quite sparse. And only one of these observations was able to do this kind of timing analysis. Now, what if instead our coverage looked more like this? Up to 16 epochs in, say, a 300-day outburst, and all of them enabled to do this kind of timing analysis. Well, that would really solve this problem. So to make this kind of a reality, I developed this multi-year large observing program that I call Pitch Black. And it connects a global network of telescopes anchored by the JCMT in Hawaii, and also includes recently accepted programs on the VLA and ALMA. Now, this program is designed to perform the same spectral timing experiment that we've done with V44, SIG-X1, and MAXI 1820, except we're going to repeat it many times throughout their outburst. And we're going to do this for 6 different systems. Now, this was supposed to start off last year, but like many things, COVID kind of got in the way. So we're hopeful to actually get underway this year and start triggering and really be able to take what we've done here with V44 and SIG-X1 and MAXI 1820 kind of to the next level. Now, this pitch black program is really designed to do this kind of systematic variability study. But you might think that this variability analysis might also be helpful in understanding sort of the more bizarre or weirdly behaving systems that don't quite follow that perfect Q-shaped pattern in HID. In particular, systems like Cygnus X3, where this system tends to go into these really massive flaring episodes that reach like Jansky levels in the radio, or GRS 1915. And this system is one of these sort of persistently accreting systems that never kind of leaves outburst. But interestingly, not too long ago, it kind of faded and went into this really low state. So we have VLA subarray observations of both of these unique and odd systems. And this is just kind of a preliminary shot of a few of the light curves we've produced, where you can see that we're already catching some beautiful variability here. And I'm hopeful that we can use this sort of timing analysis techniques to try and understand what's going on in these weirder systems as well. All right, so hopefully I've convinced you that the time domain is an incredibly powerful way to study these jets. And we're not just limited to doing time domain stuff in the X-ray or optical or infrared anymore. We can push to the longest wavelengths with today's instrumentation, where things like VLA subarray mode have been really instrumental in doing this. Now, with these kind of data sets, we can start deriving fundamental jet parameters from just the time domain alone and really get out physics that we simply can't with other methods like VLBI. There's been a lot of early successes with these kind of studies, especially driven by the VLA, but they really are still very much in their infancy. So we need to continuously improve and adapt them. Now, I hope the pitch black program that I told you about is one example of a way forward in the near future. But looking farther into the future, we can look to improve capabilities of next-gen instruments, most notably ngVLA, ALMA 2030, SKA, JWST. These are all going to play really key roles in terms of increased sensitivity and wavelength coverage. So there's a lot of exciting prospects for continuing to develop these spectral timing experiments. And instruments like the VLA and ngVLA are really going to be key in being able to drive new discoveries with this science in the years to come. So thank you very much.
Okay, so we've got one question in the Q&A that I'll start off with. Would variability studies of stellar mass black holes provide much insight into supermassive black hole variability, even though the larger mass black holes are generally not as variable on short time scales?
Yes, that's an excellent question. So that's actually just in general one of the big motivators for studying these stellar mass systems over the supermassive ones is that they're varying much faster. So we can apply, in theory, what we know from stellar mass systems to supermassive systems. But you're right in terms of the variability, it's much slower in the supermassive systems because it basically scales with black hole mass. But it's interesting whether we haven't done detailed comparisons between kind of the variability timescales and stuff like that. But if I just kind of think off the top of my head, like Sag star, we're looking at things like hours to minutes kind of thing. So yeah, that's an interesting sort of direction to go in actually starting to make direct comparisons between whether the timescales and the correlations and stuff. But with the supermassive systems, it can get quite difficult, especially when you're looking, for example, those kind of time lags, because they're going to be so much longer. So it's really hard to tell whether say you have two flares, whether they're related or not, because it's just such longer time scale. So there becomes a lot more uncertainty in doing that kind of variability study in the supermassive system. So, yeah.
Okay. All right. So I have a question from within the panel. which is if you could expand a little bit more on what ngVLA will do to enhance this area of work.
Okay, yes. So
especially the unique capabilities of ngVLA relative to some of the other ones you mentioned.
Yeah. So beyond just like the obvious sensitivity, really it's the fact that ngVLA is going to cover such a wider wavelength range all on one instrument. So like right now, to get the same kind of wavelength range, we have to combine, VLA with ALMA. But imagine if you could do all that on one instrument with ngVLA. It would make it much easier to actually schedule and make these observations happen, because, well, like a lot of amazing people go into actually coordinating everything. There's quite a fair bit of luck in being able to make sure that everything goes off without a hitch, and getting a data set like that MAXI 1820 data set with all that simultaneous data. So the more bands that we could get on one instrument, the easier it makes being able to get the kind of data sets we need, and the less risk goes into it as well. So that's really the big thing that we're going to get from ngVLA, I think.
Could I maybe add something that I think might be important, and you can maybe follow up on that? Sure. Which is the fact that there are 200 something dishes means it'll be a lot easier to subarray it and still have enough dishes to do the correlation and the detection for many bands simultaneously, instead of having to chop back and forth. Could you
yeah, that's true. That's true as well. Yeah. Having many more dishes, and that's really an interesting thing too. I wonder how many subarrays that you would actually be able to use with the ngVLA, because right now the current VLA, we can only do up to 3 subarrays. But yeah, if you could do more, then you could have more bands, and yeah, it just makes it we can get much more better data set coming out of that. Yeah. So
if somebody knows that, who's on the call, if they could put that into the chat, that would be helpful. What the maximum number of subarrays at one time with ngVLA is planned to be. Okay, so get another question. I noticed when you were presenting your jet speed estimates for the 3 sources, you had real estimates for 2 objects and a lower limit for one of them, right? Is that because 2 of them have parallax distances and one of them doesn't, or is that for some other reason?
So that the lower limit on the one system, that purple point GX339, it's there because they only had a X-ray to infrared lag was only detected, so no other lags to other frequency bands. So this is kind of like what I was mentioning during the talk, is to really get out solid estimates of the jet speed, you need multiple lags to multiple bands. So they only had the one there, so that's why it's a lower limit. Okay,
but kind of to follow up along those lines, would getting more distance estimates help constrain some of the values that you're interested in here?
Oh, yes, absolutely. So especially with the MAXI 1820 results that I showed you, we had a solid parallax distance estimate to the system. And that's definitely a key parameter that comes into modeling all of this jet emission and timing properties. So yeah, having a good estimate on the distance is key to getting good constraints on the jet parameters coming out of the model. Absolutely.
Okay. All right. And we've gotten an answer in the chat that ngVLA at the present time, the plan is to have at least 10 subarrays available.
Wow. Yeah. Okay. Well, that would, I mean, that's just revolutionized doing this kind of science. You can imagine that. Yeah.
Yeah. I mean, I think some of that is because one of the plans is that you might use the long baselines for one target and the inner region for another target. But yeah. All right. Okay. So I've got a little bit of an oddball question here. Suppose you had a broad simultaneous coverage for a gamma ray burst. Do you think you would be able to extract information about the jet properties of gamma ray bursts that way? Or do you think the non-stationarity would make it really hard to make use of these methods?
So yeah, that's a really interesting question. I've thought about this a little bit and actually talked to a couple of gamma ray burst people about it. Yeah, the non-stationarity becomes a problem. And I think also it really depends on the kind of time scales that you're dealing with. I'm pretty sure with the gamma ray bursts, it's going to be much faster time scales than what we're dealing with in the X-ray binaries. So yeah, it's still an interesting thing to kind of explore. But yeah, I think we need to have some more deeper thought about whether it's possible to be able to do the similar kind of thing with those,
Okay. All right. Now we have a question from the Q&A. The hotspots that are associated with the outbursts, are they brief or persistent? And do they align with the main axis, radio axis, or are they off axis? And do hotspots reappear at the same location each time, or are the locations of the hotspots variable?
So that's a good question. So there were a couple X-ray binaries beyond just 1820 that have shown these kind of X-ray or even radio hotspots. Now, with 1820, I'm pretty sure that there was some evidence that they moved slightly. I'm just trying to remember the paper. They were lined up with the jet axis, I believe. I think in most cases, in most of the systems, they are. And there was a third question.
And then do they reappear at the same location each time, or are the locations variable?
So I'm trying to think. I don't know if they've been, I don't know about the X-ray hotspots. I know that in a couple of systems, sort of radio hotspots that have like appeared earlier in outbursts and then disappeared and then appeared again. And I'm pretty sure that those have moved as well. So that's consistent with the idea that these kind of hotspots, they are like shocks between, the jet material smashing into the surrounding medium. And, if we are carving out some kind of cavity, then I guess theoretically you would expect that to move. And if you're moving material out of the way and that kind of stuff. But yeah, I hope that answers some of those questions.
Okay, maybe I can add a follow-up question about some work that you've done that you didn't talk about here, which is, would you expect ngVLA to help you detect molecular emission from some of those hotspots if those are dense clouds in the interstellar medium that the jet is just crashing into? And what could you learn from seeing different kinds of molecular emission?
Oh yeah, so that's an excellent question. Thanks for reminding me of that. So what we've done so far is we've used ALMA to detect, sub-millimeter emitting molecular emission lines in a couple systems where we expected that there was going to be this kind of jet ISM sort of interaction. And we have detected these kind of bubble cavities around a couple of these systems. Now, if ngVLA, we're going up to right around just over like 100 gigahertz, I believe, somewhere around that.
It's set up to just barely be able to do CO.
Yeah. So there are quite a nice sort of suite of molecular lines that kind of show up in that kind of band 3 ALMA range that I think might actually be possible to do with ngVLA. So that's that could be really interesting, especially with the kind of sensitivity and the range of angular scales we'd be able to probe. So that's definitely another kind of interesting X-ray binary related science case that I think ngVLA could really help out with too. Yeah.
Okay, neutron star systems tend to be weaker in the radio. What would it take to study them like you've done for black hole systems?
So that's a really good question. We haven't really done these kind of detailed variability studies with neutron star systems yet, because like you say, they are much fainter. Although there are a couple of systems like SCO-X1 that are going to be much brighter than your kind of typical neutron star system. That would probably be sort of a good kind of first test to go after. I think it would be possible to do with the VLA these days, but going after these kind of maybe more persistent, brighter neutron star systems first to see, as a test, kind of what we can actually detect on these kind of short time scales would be a good way to go first. And then, especially as we move into the ngVLA era, it will definitely be possible to be probing variability in even like these really faint neutron star systems as well. So that should be really interesting too.
Thank Alex again for a wonderful talk.